Okay, we're going to find out if this series here converges or diverges. We're going to find out if it converges or diverges by doing the integral test. We do the integral test with this thing because, well, there's always two reasons with the integral test. The first reason is that this is monotonically decreasing. That means that the sequence, no matter what you plug in, each successive term is going to be smaller than the previous one. That's what it means to be monotonically decreasing. So you're looking at the sequence, not the series. The series is going to be increasing because no matter how small the numbers you add become, you're still adding. So the sequence is decreasing, and the sequence is always positive. You don't have negative terms because we're plugging in numbers from 1 all the way to infinity. So for that reason, we could do the integral test with this. So let's do that. So this is 1x squared plus x cubed dx. With this one, we're probably going to want to solve this integral by partial fraction decomposition. And why are we even doing an integral? Just to find out if this converges or diverges the series itself, because if the integral converges or diverges, the same is true for the series. So let's do the partial fraction decomposition. This would be 1 over, we factor x squared, so we're left with 1 plus x in there. And with this, of course, we're going from 1 to infinity, but we can't really do infinity directly. So we have to replace this with a t and use a limit. So the limit as t approaches infinity, and the limit as t approaches infinity. Okay, now how do we do our partial fraction decomposition? Well, we have two things we're multiplying here. One is squared, the other one is not squared. So the one that's squared goes under bx plus c. If we remember, that goes under bx plus c. The linear one, the one that doesn't have anything squared, goes under a. We add these, and this numerator should equal that. So this should equal 1. Now we can cross multiply. This will give us ax squared plus bx plus c times 1 plus x. We can distribute that, and we get bx plus bx squared plus c plus cx. That's next. So now we get all the terms that are alike together. We have some x squareds over here. We got a and b are going to be multiplied to x squared. We have b and c multiplied to x. So b plus c are multiplied to x. And we just have c as the only constant. So with this, we know what's going to be 1, right? Now we know what's going to be 1 because c is the only thing that doesn't have an x or an x squared. And so these guys must go to 0 because we don't have x squared in our numerator. We don't have an x in our numerator. We do have a constant. We have 1. That must be c. So c equals 1, a plus b equals 0, a plus b equals 0, b plus c also equals 0. Now we can plug in 1 into that. That gives us b equals -1. We plug -1 into here. That gives us a equals 1. Now we have our new integrand. This is 1, that's negative, and c is 1. So this is our new integrand, and we can now solve this. We can now solve this much easier. limit as t goes to infinity. It's really two pieces now. This is what we wanted. So we can always add these integrals. We can always split them into and add them. So for this one, we can already solve. And the limit is to the entire thing, by the way. And we need a dx here. Dx. So for this one, we can already solve. This would be the natural log of the absolute value of 1 plus x. That's in the denominator. That's what goes inside of the natural log when we integrate. We have integrated that. With this one, before we integrate, we should split it into another two integrals. With this one, we're not going to need partial fraction decomposition because the addition is not taking place in the denominator. The addition is taking place in the numerator. That means we could just straightforwardly split this into two different integrals. We have negative x over x squared dx, and then we're adding the other integral like this. So this would give us what? Negative 1 over x. They both lose an x. And for this one, okay, let's evaluate this. So this would be easy. This is the negative natural log of the absolute value of x. With this one, you might be tempted to do the natural log of x squared, but that's not how you do it. And it's easy to forget that. But with this one, this is x to the power of negative 2. So we evaluate that integral by just adding 1 and then dividing by whatever exponent we get after adding 1. That's how we do integrals. So it's only the case when it looks like this or when it looks like this, not when it's squared. So this would give us negative because we add 1 and then divide by that. And anything to the negative 1 power goes in the denominator. So this would be to the negative 1 power, and then you divide by that. So that's how that looks. Bring this one down. 1 plus x. We're taking the limit as t approaches infinity of all of these. And we have to now do our bounds. Our upper bound is t. Our lower bound we get from here is 1. Okay, so now let's actually perform that subtraction to see what it converges to or if it diverges. So we're going to perform a subtraction. So if you remember, we take the upper bound and then we subtract from that the lower bound. The upper bound, we're going to plug in t's for all x's. Natural log of 1 plus t minus, I'm going to need more space, minus natural log of the absolute value of t minus 1 over t. And now we do with 1, so this would be natural log of 2 minus natural log of 1 minus 1 over 1, which is 1. Let's plug in infinity and see what happens. So we plug in infinity into here, and we would get the natural log of infinity because infinity would swallow the 1. It doesn't make a difference. So that's the natural log of infinity, and the natural log of infinity goes to infinity. And this would also go to infinity. And so we're subtracting. We have infinity and we're subtracting infinity. So when we have a situation like that, something weird is going on. You can't just assume with the natural logs and they're going to infinity. You have one infinity, you're subtracting another infinity. You can't just assume it goes to 0. You can't just assume. It does. They do go away because they're very similar, so your intuition would tell you, hey, they're similar infinities and you're subtracting them. So it should just go away. And your professor wouldn't be happy with that. They would probably want to see you actually show it. So remember natural log properties, if we're subtracting, you're actually dividing, like this. So this is what we have. Now we can look at what we have inside, and which is 1 plus t over t, and we can divide everything by t, because we have t here, t there. So we divide everything by t. Now do our limit. As t approaches infinity, this would go to 0, got infinity in the denominator. This is 1, and this is 1. So you have 1 over 1 when you take the limit as t approaches infinity, that's just 1. So we have the natural log of 1, after all. This entire thing, it actually represents the natural log of 1. What is the natural log of 1? Well, remember, this is log base e of 1. So what does that equal? It has to equal 0. Because e to the power of 0 is the only thing that could give us 1. So the natural log of 1 is 0. So yeah, our intuition was correct. We have an infinity and we have a similar infinity. If we subtract them, we get 0. But we had to show that. So this becomes 0. And this guy obviously becomes 0 because we're plugging infinity into a denominator. So this is all 0, and you're left with this answer, which is negative natural log of 2 plus the natural log of 1 plus 1. And this converges by the integral.